Welcome to the final exam review for ECE 501B. The process for the final exam, I hope, is no surprise to anyone. There's 4 sheets of notes. You can bring a calculator, something to write with, but then everything else is a no. No computer, no cell phone, no textbook, no class notes. You do get 4 pages of notes, and that's effectively 8 sides of 8.5 by 11 sheets of notes. In terms of material, wow, went beyond the width of the page, but it's really the first textbook that we were using, Axler. Chapter 4 was on polynomials. We really didn't cover that, but we did pull some needed information from that, and we'll talk about that maybe as we go through. And 8 and 9, that was this operators on complex vector spaces or real vector spaces, and the main thing we brought out of that was the generalized eigenvector, or that notion, and that's what I'm wanting you to take from that. And then first 2 chapters in the textbook by Axler. Those are the chapters in the textbooks of this course that you're responsible for. I thought I would provide you with maybe a strategy on how you can study or prepare for the final. I know time is short. If time was not short, I would say go back and read both books cover to cover and then look at your notes and then look at the homeworks. So I'm actually doing it almost the exact opposite. First, you might look over the previous exams. Then you should start looking at what happened since exam number 2. And the final exam I'm anticipating will be comprehensive. I haven't yet decided what it will look like. Guess I need to write it. We do, oh, I should say our final exam is Monday, isn't it? Monday the 16th from 6 p.m. to 8 p.m. in room ECE 107. So that's our final exam. You've now studied the previous exams. You've looked at homework 7, which was the one homework beyond, or we had homework 8 too, didn't we? Homework 7 and 8. I'm a little bit hesitant to write on this because it seemed to be messing up before, so I'll see how it does. I think I'm going to start a new page in a minute. But homeworks 7 and 8 since exam 2, and study the work, I guess it's chapter 7, chapter 8, and chapter 10 material in Axler and the examples from Franks. Then I would probably start to review the homeworks, all of them, and then read through the class notes. And then if you have some sticky points or something that's not very clear, then go back to the textbook and start rereading that. And I hope now it begins to make a little bit more sense than the first or the second or the 5th time that you read that material. Hopefully now that you've seen the course, which now I'm saying is sort of this big picture view of what 501B is about, you can now step back into the textbook and better understand or appreciate what it is that's trying to be explained. That's the strategy for studying for the final exam. You have a few days, Saturday, Sunday, and Monday. You may have to chop up your time depending on how many other finals you have, but you have until 6 p.m. on Monday to prepare for this final exam. In terms of the way to think of this, I wanted to say a pyramid, but then I said really we kind of, and it's easier to write from top to bottom. So I said just think of an inverted pyramid or triangle, and we're really focusing more or getting more specific as we go to higher and higher chapters. This is basically for Axler. The first piece, the big foundation of this, is vector spaces. And then we said let's specialized that to finite dimensions. Then we started learning about linear maps, and we finally ended up down here with matrices and understanding a little bit more about determinant and the trace of a particular map, and in particular a matrix A. A lot of times linear algebra classes start with the determinant and the trace, or the determinant, and then build up from there. But this particular approach tries to build on a strong foundation from vector spaces and then march and down to a finer focused topical discussion. And that's, I think, one way to sort of view or think about what's going on with respect to this course, in particular the first part of the course, which was dealing with the finite dimensional case. And the infinite dimensional case, you could sort of duplicate this shape and say, oh, instead of vector spaces, now we have signal spaces, and we start introducing length and angle on that, and we just keep going down, down, down into more information on infinite dimensional spaces. Let's now talk maybe from a fairly high altitude, but I wanted to sort of give an overview of the course so that now as you're reviewing for the material, it maybe starts to, oh, now I see how it's all related, and you can start to put all the pieces together. That's the plan. So if we walk through that inverted pyramid, we started with chapter 1, which was dealing with vector spaces. And with respect to vector spaces, really what you have are three pieces. You have a set, and you have addition, and you have scalar multiplication. And you put those three pieces together in a particular way, in the fact that a vector space has to have 6 particular properties associated with it, or satisfy 6 things. One of those being the associativity property, another one being the, whoops, I can't read my own handwriting. The second one is associativity. The first one is actually the ability for these sums to commute. So commutativity, associativity. Then you need a additive identity, which is really just a zero element. You then need an additive inverse, the ability to add something that will get you to the zero element for every vector. And now vector is in this quotes, it's a more general idea. Then you need a multiplicative identity, a 1, a scalar 1 from your field. And finally, it needs to have these distributive properties where you can distribute a scalar across 2 vectors, or you can distribute 2 scalars across a vector. So those are things dealing with vector spaces, and in here you're sort of viewing 3 different pieces that you need: a set, closed, or an addition, and a scalar multiplication. Once you now have a vector space, you can actually start partitioning that or breaking it up, and you get this idea or notion of subspaces. And if you have a subspace U, or let's say that you just have a subset U and you want to determine is that a subspace, then we know that it inherits all of these properties of the vector space. And to show that it's a subspace, you just need to check 3 things. It really doesn't have to be checking all of these. So you need to check that it has the additive identity, or a zero element. It needs to be closed under addition. and it needs to be closed under scalar multiplication. If you have those three checks on this subset U, then it's a subspace. One of the main ones is it needs to have that identity element, or the additive identity, the zero element. Then the last part of, maybe I shouldn't put that plus sign, let me say sums and direct sums in chapter 1. The direct sum allows you to express V, any element in V can be written uniquely from some piece of each of those subspaces that make up the direct sum. That's the only way that you can write a V, is uniquely from an element or a vector in the subspaces making up that direct sum for the total subspace V. That's chapter 1, the main ideas behind chapter 1. Then we start to focus down and we say, let's just restrict our attention to finite dimensions. Or finite dimensional vector spaces. And that allowed us to really introduce some new ideas, mainly what do these vectors span? Are these vectors linearly independent? And hopefully you remember what that means. If you add them up, then the only way you can get 0 is for the coefficients or those scalars to all be 0 for a set to be linearly independent. You could then find a number of those linearly independent vectors that fill up the entire space or the dimension of the space, and that would then give you a basis. And those are the 4 key pieces of chapter 2. Span, linear independence, basis, and dimension. How big is this? And that's sort of counting up how many vectors you have in a subspace or a vector space will be the dimension of that space. Now, just playing on spaces may not be so fun, so we learned how to map between the two. That was chapter 3, which is now, and we specialized those maps to be linear. And to be a linear map, we needed this 2 things, really, additivity and homogeneity. And once we had those, then we have this linear map. Once we have maps, we could start talking about vectors that map to the 0 element or the null space, non-trivial vectors, and we could start talking about range space. So null and range are 2 big things for these linear maps, let's say T, that are mapping not necessarily between the same space, but from V to W, 2 separate vector spaces. And we're dealing with finite dimensional vector spaces. We then started learning about injective maps and what that means, and a map is injective if and only if it has a trivial null space. The null space is the only element or vector in the null space is the 0 vector, then your map is injective. Or you could call it a 1-to-1 mapping. Then we talked about a map being surjective, and that meant that the range of that map, or where you could get to, was actually all of the codomain that you were trying to get to in W. And that was then another way of thinking about that is that that's then an onto map. And there are many different ways of allowing some of these ideas to be connected. In theorem 3.4, if T is this linear map from V to W, then this particular theorem gives us a little bit of information about how we can relate the dimensions of those. The dimensions of the underlying domain space, V, dimension of V, is now equal to the dimension of the null space of that map plus the dimension of the range space of that map. And if you're playing with maps and you need to start checking certain things, this relationship might be important if you have certain dimensions, and then you can maybe say something about what's going on in that particular with that linear map. Also, when we start talking about matrices as linear maps, we also looked at a proposition 17 in chapter 3, which says that a linear map is invertible if and only if it's the other two, on to one to one and on to, or it is injective and a surjective map. So it's one to one and on to. And if we have an invertible map between two different spaces, then those two spaces are related, or they are isomorphic. That's the word that we use to describe those two vector spaces. Meaning in a picture form, we could say, oh, if we have some vector space V mapping into another vector space W via some map T, if this is an invertible map, then we actually say that V is isomorphic to W. So these vector spaces basically are the same in an underlying sense. They're isomorphic. That's a way of viewing that. So these vector spaces are isomorphic, which means that we now have a way to go from V to W and also a way back through the inverse map to go from W to V. Or V and W are isomorphic vector spaces. Now, if we specialize in chapter 3 these linear maps to be mapping between V and V, then we call those linear maps operators. We specialize it to say, oh, now we introduce this new concept of an operator which says that we now have T going between V and itself and V. Or sometimes we might even abbreviate that to say it's a linear map on V. And once we have a finite dimensional vector space, then theorem 321 says that T, or the following three statements are equivalent. T is invertible, T is injective, and T is surjective. Those are equivalent statements in a finite dimensional vector space. Infinite dimensional, then that doesn't hold true. But that's what we learned in chapter 3. So we have a way of moving between vector spaces provided to us by introducing these linear maps. That was chapter 3. Then we started thinking, oh, we kind of like this idea of an operator, because now maybe we can do even more or talk more about what's happening. And before we did that, there was sort of this insertion in the book, chapter 4, on polynomials. But the main thing that we wanted from chapter 4 was theorem 4.7, which is actually the fundamental theorem of algebra. And that one says that every non-constant polynomial with complex coefficients has a root. That's a pretty powerful statement. Any polynomial that's non-constant, so if it's something that has a polynomial term, first order, second order, third order, it has a root. Now, if the coefficients are real, then that's not quite the case. That's where we might end up with quadratic factors that don't give us a single root or roots at all in the real space or real setting. So that was the main thing that we pulled from chapter 4 on polynomials. We really didn't dive into that. And then we started saying, oh, now that we have this idea of polynomials, we can start to look at how operators, since they're going between themselves as far as vector spaces, we can sort of view these operators in terms of polynomials or have polynomial operations on these operators, which chapter 5 then says, oh, now we're into this idea or concept that is referred to as eigenvalues and eigenvectors, which means that we're dealing with square. If we were viewing it as the matrix representation, we now have the opportunity to talk about eigenvalues and eigenvectors. These are operators. And again, this is on finite dimensional vector spaces. One of the key things, though, when you think about an eigenvalue, well, really when you think about an eigenvector, or eigenvectors, then we're dealing with invariant subspaces. And that's sort of the key phrase or concept to think about when you're thinking about chapter 5, eigenvectors. Now, if you operate on that direction or that vector with a linear map, then you're going to stay on that same vector or in that same orientation if it is an eigenvector. It's an invariant subspace. Then there were many different theorems in chapter 5. Some are that in theorem 5.6, if we have distinct eigenvalues, let's say lambda 1 through lambda sub m, then the corresponding eigenvectors are actually linearly independent. So if you need to find some linearly independent eigenvectors on a particular space, you could do that by looking at the eigenvectors associated with distinct eigenvalues of a linear map. Theorem 5.10, every operator on a finite dimensional non-zero all of these adjectives are important, but the main one is complex vector space has an eigenvalue. And that's not necessarily true on a real vector space. We could have invariant subspaces, but we may not have an eigenvalue. But here, theorem 10 in chapter 5 says every operator on a finite dimensional, non-zero complex vector space does have an eigenvalue. (513) If V is a complex vector space, then we can actually form or produce an upper triangular matrix representation of a linear map. The real version of that is not quite as clean. Now we sort of are dealing with block upper triangular, because now if we have real vector spaces, we now have invariant subspaces of dimension 1 or 2. And that's chapter 5, invariant subspaces, and what we get when we look at complex or real. And typically we get more for our money on complex vector spaces than real. Real usually introduces more restrictions. We still haven't really talked much about length and angle, and that's why we moved into chapter 6, which was to refine our space that we're living in a little bit more. So we're going closer to this inverted triangular shape that I started with. Now we have inner product spaces, and what you might be keeping in mind here is that we now have this idea of length and angle if we have an inner product. And inner products enjoy certain properties. And you need to sort of be able to know that or understand that. One is positivity, meaning if you take any vector and form the inner product with itself, that needs to be non-negative. It also needs to be very definite, or there's a definiteness property which says that if you have V with itself and that forms a scalar, this inner product takes two elements from your vector space and maps those into a scalar. Now if you have a vector and you inner product with itself and that inner product ends up being a hard zero, that's true if and only if V, the vector, was actually the zero element to begin with in that vector space. 3, as far as a third property for an inner product, it has to have additivity in the first slot, which means if we had U plus V inner product with W, that's similar, or that's equivalent to forming these other two inner products. We also have the property of homogeneity in the first slot, which says that if we have some alpha scaling V, then in the first slot, that can just slide right out of the inner product. And we have that scalar then scaling the inner product of V with W. And finally, if we're dealing with complex vector spaces, then we have conjugate symmetry of the inner product, which says that U inner product with V is, whoops, it's really going to be special if we do that, isn't it? It's the complex conjugate of the reversal of the two vectors in the slots. And once we have that, now we can, once we have defined an inner product, and we could have all sorts of inner products, just like Wednesday we were talking about different distances or metrics in the infinite dimensional case. That's sort of what these inner products are, and we've defined different inner products. Some were integrals, some we were just sampling these polynomials in a traditional vector sense. We might have a row times the complex conjugate of a column, so to speak, to get a scalar. But once we have an inner product, then we can create an inner product space, which is really simply saying that we now have a vector space with an inner product. And once we have that, now we have length and angle. And once we have angle, we can start talking about things being perpendicular or orthogonal to each other. So now we have this orthogonality concept that is available to us, and U would be orthogonal to W if their inner product is 0. Then we can go back many hundreds of years to Pythagorean, or the Pythagoreans, and play with the Pythagorean theorem. Or use that so that now we have U plus W squared is equal to U squared plus the norm of W squared, or the hypotenuse distance squared is equal to the sum of the sides squared, because those sides in a right triangle are orthogonal. But we can generalize that idea to higher dimensional vectors. Once we have orthogonality, now we can actually write vectors into like an orthogonal decomposition. Meaning if we wanted to rewrite U as a component along V and then something orthogonal to that, we looked at how we could do that, and we basically now take the inner product or correlate U with V, find how much U and V basically overlap or are in the same direction, divide the length squared of V out of that, and that's now the percentage or the proportion of U along the direction of V. And then we have the orthogonal component, which is the difference between U and what we just said was in the direction of V, which is now this UV inner product divided by V squared in the direction of V. Or you could think of this now as a piece alpha along V, and here is your orthogonal component W. And that produces, or that provides, a rich resource to use when we even go further and extend this in multi-dimensions. But even here, now we can start, once we have these inner products, we have all sorts of different inequalities and equalities. We have the Cauchy-Schwarz inequality, which says that the absolute value of the inner product is less than or equal to the norm or the product of the norms of u and v, we have the triangle inequality, which basically says that if we were dealing in a two-dimensional plane, any two sides of the triangle have to be bigger or longer than the third side. So this now says that we have, in a vector sense, generalizing that, we say u plus v's norm is less than or equal to the norm of u plus the norm of v. Those are inequalities. We actually found that we have some equalities. And when I think of this one, I just think of the back of an envelope, meaning now I sort of have this picture in mind, and maybe you want to skew it a little bit so that it makes it a little bit more interesting. But now we have these diagonal pieces, their norm squared and added up, are equal to the norm of the perimeter, essentially, or twice the length of u squared plus the norm of v squared. Then we have, once we have length and angle, we can start building up basis vectors that are orthonormal. We can get them to be orthogonal, and then we can normalize them by dividing by their length. That now gives us orthonormal basis. If somebody gives us some linearly independent vectors, we can use the Gram-Schmidt procedure to create an orthonormal set of basis vectors. Once we have all of that machinery, now we're able to look at some minimization problems. And that you could view as some projection of a vector v onto some smaller subspace, capital U, for example, where we're now, if E1 through E sub m are orthonormal basis vectors for this subspace U, then we can take the projection of v on each of those orthonormal basis vectors and add them up. And each of those scalings or inner products are weighting that particular direction in this subspace U. So this might be v e sub m, e sub m. Boy, that's pretty poorly written m, so let me try to correct that. Not much better. But now that we have this idea of inner product, we can extend that or apply that to two more concepts from in chapter 6, one being linear functionals and the other being adjoints. In terms of linear functionals, we might have some generic linear functional phi that takes some high-dimensional vector space, n-dimensional, into some scalars, real or complex. That's some map. But that's then, we learned, equivalent to finding an inner product. We can say that phi operating on u is the same as u inner product with a vector v, where v is now formed from taking this linear functional and applying it to each one of the orthonormal basis vectors of capital V, and then using that as a weighting on each of these directions, or orthonormal basis vectors. And that also is a very powerful concept. And in the book, I think they looked at how you could use that to maybe approximate a cosine waveform, for example, with a much lower order polynomial than you might be expecting from some other approximation technique. The adjoint was defined then in terms of an equality of inner products. If we have a linear map T operating on V, an inner product, and taking the inner product of that with any W, then we said let's define an adjoint operator that gives us the same scalar or gives us the same result in an inner product sense as the inner product of V with this linear operator T something operating on W, and we called that the adjoint, T dagger. T dagger then was defined to make these two inner products equivalent or equal. And then near the end of chapter 6, it actually gave us a proposition that allows us to equate certain properties of these two operators and their respective subspaces. Proposition 646, taking this linear operator between V and W, then that actually allows us to say that the null space of the adjoint is going to be the same as the orthogonal complement of the range of T. So if we needed some vectors for the null space of T dagger, then we could find the range of T, find the orthogonal component, or a basis for the orthogonal component, and now we have a basis for the null space of T dagger. And there's other relationships. We could look at the range of T dagger, and that's now the orthogonal complement of the null space of T. And then we have the other two pairs that are concerned with the null and range space of the original linear map T. The null space of T is now equivalent to the orthogonal component of the range space of the adjoint. And the only other one we haven't looked at is the range space of T, and now you can anticipate what that's going to look like. That's now related to the null space of the adjoint in the form of its orthogonal complement. So that's now a relationship on those operators, the linear map T and its adjoint. And if you're given one, then you can start to build up basis vectors actually for the other in terms of where they belong. One of the last things in chapter 6 concerned how we might create the matrix representation of the adjoint. But this was only very specifically determined, wasn't it? We have to have orthonormal basis vectors on both. The space of the, let's say, V and W on this linear map T. So as long as we have orthonormal, and that's plural, bases, meaning we have orthonormal bases on V and W, then we can say that the matrix representation of the adjoint of T can be found by taking the complex conjugate transpose of the matrix representation of the original linear map T. So if we were dealing on the standard basis, you could do it. If both V and W were defined to be the basis vectors being the standard basis, then this is true, this proposition 647. That's chapter 6, which said, oh, now we can deal with angles and distances or lengths. Then chapter 7 said, well, let's put some operators on top of those kinds of spaces, spaces that still contain now contain inner products. So now we've advanced beyond chapter 5 because now we have a different playing field, so to speak. It's now this inner product space. So chapter 7 was talking about operators on inner product spaces. And now we can start identifying or introducing all sorts of new terms or different kinds of operators. One of those, again, an operator is mapping from V to V. So playing in that space, we can now say, oh, and we also can measure distances and angles because we're on an inner product space. So V is now an inner product space. If we have a self-adjoint operator, that says that the operator is actually equal to its adjoint. That's self-adjoint. And now you can start to think about analogies with respect to complex numbers now that we have that. So if you're, and I don't know where to put this, maybe I'll try to, I don't want to hide it. I actually want to sort of emphasize it, and first I have to spell it properly. But if we viewed the analogy that we have a complex number corresponding to a linear map T, now if we have a self-adjoint operator, or maybe I should say the adjoint is similar to the complex conjugate, and once we have the fact that Z is actually real, that says now that we have a self-adjoint operator. So this is now saying that Z is equal to Z star. And now we have many different results. Proposition 7.1 says if we have a map that's self-adjoint, if T is self-adjoint, what do we know about the eigenvalues on that map? They're all real, aren't they? Corollary 7.3, if T is self-adjoint, or T is self-adjoint, and now we have an if and only if and only if this inner product of T with V is real. And now you can think of what that inner product does, and that's true for all V in capital V. Then, like I said, we're starting to introduce a lot of new terminology. We just introduced self-adjoint. Now we can sort of generalize that and say, what about these operators that we're going to call normal? And these are not self-adjoint, but all self-adjoint operators are normal. But we could have normal operators, which says that now the operator and its adjoint commute. Another result that's a pretty powerful result is that the norm of TV is equal to the norm of the adjoint with the same vector V. And that particular result actually says that the null space of the linear operator t is the same as the null space of its adjoint. And that's a really good or nice connection to have. And that was made in a marginal comment, basically, in Chapter 7. But once you know you have a normal operator, now you know something about the null spaces of the operator and its adjoint. They're actually equal. They're the same space. Then we have, if t is normal, then we can actually say something about the eigenvalues and eigenvectors between the operator t and its adjoint. And I don't know how to really say this very clean or very succinctly, but let's say that we had an eigenvector v and an eigenvalue lambda sub I, and if t is normal, then the adjoint has the same eigenvector, but the eigenvalue is now the complex conjugate. Again, relating the operator with its adjoint. Then we have, now that we've introduced concepts of self-adjoint and normal, we can start talking about the spectrum of such operators. And that produces these spectral theorems. Meaning, if we are dealing on, if V is a complex inner product space, and this linear map T is living or working on this complex inner product space V, then V has orthonormal basis consisting of the eigenvectors of T if and only if T is normal. So if we have a normal operator and we're living on a complex inner product space, then we know that we can find an orthonormal basis set by just finding the eigenvectors of that linear operator. Or if we find that we found an orthonormal basis and they're the eigenvectors of a linear map T, then we know that T is normal. That's an if and only if relationship. That's on complex inner product spaces. It's not quite as, well, it's more restrictive once we move into real inner product spaces. And here is now the real. So this was the complex spectral theorem. We also have the real spectral theorem, which says the following. If V is a real inner product space and T is a linear map on that real inner product space, then V has an orthonormal basis consisting of eigenvectors of T Now I said it was more restrictive if and only if T is not normal. It now has to be self-adjoint. It has to be better than normal. It has to be self-adjoint, or the operator has to equal its adjoint. Then we can have, on a real inner product space, an orthonormal basis consisting of eigenvectors of T. I said chapter 7 was full of definitions, didn't I? We've had self-adjoint, normal, then we made it into these spectral theorems. Then we started learning about positive operators. So if T is an operator on as a linear map or a linear operator on a vector space V, that operator is positive if T is self-adjoint, T is equal to its adjoint, and the inner product is non-negative, TV with V. Then we have a positive, some people might say a positive definite operator. Here we have a positive operator for this book. Then we have different relationships or ways of thinking about what we have when we have a linear map that's positive. Here are some equivalent statements coming to us from theorem 727. T is positive. And this is basically from the definition as far as T is self-adjoint. That's from the definition of a positive operator. But now we know that all of the eigenvalues of that linear operator are non-negative if it's a positive operator. We also know that we can find a square root of that linear operator where that square root is positive if T is positive. So if T is positive, then we can find a positive square root for that positive linear map. We can also find a square root where the square root is self-adjoint. And if somebody gives us a linear map, T, and they say it's positive, then we know there exists an S, another linear map, such that T can be factored as S, the adjoint of S times S. That's a positive operator. Then we talked about, or learned about, an isometry. Isometries preserve norms, meaning if we have the norm of SV, that's equal to the norm of V. We're not expanding or contracting the norm relationship. And that's true for all V in your vector space, capital V. But this actually says that all of the lambdas, magnitudes, are equal to 1. All the eigenvalues have magnitude of 1. If they're complex, we find the magnitude they now live on this unit circle. And now we can go back and start to even look more at this analogy chart. We can say if this is now, let's say, a magnitude of 1 for this complex number, now we know that we have an isometry as far as a linear map. If S is an isometry, then it also is injective. And once we have that, and the fact that we're dealing with finite dimensional spaces and this equivalence of invertibility, injective, and surjective, now we know that every isometry is invertible. just like theorem 727 gave us all these different ways of thinking about positive linear maps, there was a similar theorem for isometric or isometry relationships, or relationships between isometries and their adjoints. And that was theorem 736. And I think that had, I don't know, J or something. It had a really long list of those relationships. This now gives you the isometry relationships for S and its adjoint. The reason why we looked at positive operators and isometries, now we can start to think about complex numbers and what they transfer or translate, or their analogy, into linear maps. Meaning, now we have theorem 741 dealing with a polar decomposition. Meaning, if z is some complex number, we can always multiply anything by 1, and this now is supposed to be 1, the length of z over the length of z. But now we can sort of partition or move that around so that we now have z over its length times its length. But we can also write its length as the square root, positive square root of the conjugate of z with itself. And that now is begging us to do another analogy. If we now say z, a complex number, can be written as z over its length times the square root, positive square root of z star z, or z conjugate z, this now represents a direction. This now represents a scaling. And if we view this as an analogy, the complex number z is now the linear map T, but T now can be written as a direction, an isometry, and a scaling, which is a positive operator. So here is now our scaling, and here is our positive operator. So every linear map can be viewed as a polar decomposition, similar to how we have a polar factorization of any complex number, or a polar representation of a complex number. And once we have that, then we started talking about the eigenvalues of this positive operator, the square root of t dagger t. And we called those singular values, where the singular values of t are the positive square root of the eigenvalues of t dagger t. And this, as an operator, since it's positive, we can find orthonormal basis vectors for it. And the eigenvalues now, if I call those S, this is now our positive operator. Then theorem 746 gave us a way of decomposing any linear operator t that might map through a vector v as the singular value S1, v inner product with E1, scaling another direction, F1, where the E's are now what I just wrote up above for the positive operator, and the F's, which I will write underneath, the F sub L's are now related to some isometry map operating on E sub L. So this just rotates one orthonormal basis into another, which we're now calling F's. And we now have this plus S sub 2 V E2 F2 all the way to S sub n V E n F sub n. And that's another way of thinking about singular value decomposition, which is a little strange because now we have two different basis vectors with the same operator t. We have something on the input side, the e's, and something on the output side, the f's. But the e's say, how are you coming in to me? And then the f's are saying, here's how I'm going to put you out into a particular codomain, or where the range is going to be. And we talked about if you have a matrix A and you perform its singular value decomposition, then the range of A is related to vectors in U. U and V have orthonormal vectors. This is now the range of U1, and the null space of A, well, maybe I shouldn't say the range of U1. That's really what it is, but let me just say the span of the vectors in U1. The null space of A is spanned by the orthonormal vectors in V sub 2, where U1, V2 come about by the non-zero singular values in sigma, this rectangular, potentially rectangular matrix. Chapter 7 was pretty big, wasn't it? Or had a lot in it. Self-adjoint, normal, positive, isometry. Then we have all these analogies. So if you get lost, just go back to your table of analogies and say, oh, I have a complex number, that's a linear map. Oh, it's conjugate, that's its adjoint. Oh, I'm dealing with an isometry. Oh, the eigenvalues have to have a magnitude of 1. That's just a direction. Positive operator, that's just scaling in some way. And then every map can be thought of as a scaling and a rotation or a direction. That's chapter 7. All of this because we now have operators on an inner product space, and that inner product space allows us distance and angles. That's why we can do direction and why we can scale. And we can orthonormalize all these vectors. Then, for whatever reason, he puts generalized eigenvectors in chapter 8. So chapter 5 is just the generic eigenvectors, but then we go, wait a minute, we're not spanning all of the space possibly when we have repeated eigenvalues, and that's why we have to introduce the concept of generalized eigenvectors. In particular, we have t minus lambda I, let's say to the jth power times v is equal to 0. And if we can find these that live in that null space, those are the vectors that we call our generalized eigenvectors, where lambda is an eigenvalue. Then we can think about the dimension of the subspace of t minus lambda I raised to the dimension of v. And that's going to give us basically the null space associated with a particular eigenvalue, or the multiplicity of that particular eigenvalue. And once we have the multiplicity of all of our eigenvalues, then we can talk about a characteristic polynomial being created by taking z minus lambda 1 with multiplicity d1. So if lambda 1 is only 1 and it's not repeated, d sub 1 is 1. And then we just go all the way up to however many distinct eigenvalues we have, lambda sub m, and raise that to its multiplicity, d sub n. Sort of jumping ahead, we also learned in chapter 10 how that characteristic polynomial could actually be found by looking at the determinant of zi minus, well, maybe I should, let me do it this way. And I may get sloppy with notation, but now the matrix representation of a linear map. And typically I might call that A. But we now have the determinant of zi minus A. This is now coming to us via chapter 10. So I'm jumping ahead a bit. This is actually theorem 1017, but it's related. It is the characteristic polynomial. If you wanted to find it, you could find it several different ways, where T is some linear map on V. Question?
So for the eigenvalue, eigenvector equations, now we can use that instead of the actual solving.
So now the question was, when we start playing with eigenvalues and eigenvectors, I think the question was, can we use this determinant expression to find our eigenvalues instead of having to sort those out through the eigenvalue-eigenvector relationship that we've done in chapter 5? And the answer is yes. So now you can use this to find your eigenvalues, and now once you have your eigenvalues, you can try to find your eigenvectors from those null space equations or relationships, either from here. Well, this will give you generalized eigenvectors, so you need to look at the wording. If I say find eigenvectors, then you can only look at the null space of t minus lambda I when j is equal to 1. But if I say generalized eigenvectors, then you can look at the null space of t minus lambda I, where j, if you just need to find them all quickly, let j be the dimension of your entire vector space if you wanted. That might be 10, but you may not want to raise it up to the 10th power. You may want to see, maybe you now know the multiplicity of your eigenvalue, you raise it to that multiplicity. And then you find the vectors that are in the null space of t minus lambda I. Did that answer your question? So now you can play with all of this information that you now have. One more thing in chapter 8 is the Cayley-Hamilton theorem. And that says actually that this characteristic polynomial, or that the linear operator, this is maybe an abuse of notation, but the linear operator satisfies its characteristic polynomial. So if you have this characteristic polynomial in Z, if you put T, or the matrix representation of T, in where that Z is, that's going to give you an identity relationship. Question? So now, what is the importance of this theorem? This theorem actually allows you, if you wanted to potentially rewrite, let's say you needed an expression for t to the 5. Then this Cayley-Hamilton, if it's a fifth order polynomial, you have t to the 5 written in terms of lower powers of t. That's one real crude way of thinking about what good does this do, but this actually provides you with a lot of insight into how t behaves, or what t is doing relative to its powers. So you could find different relationships. This is now the fact that the operator, this t, satisfies its characteristic polynomial. And if you look at the Cayley-Hamilton result, then you'll find other nice reasons for maybe utilizer applications of that result. But that's one that just comes to mind. That's chapter 8. We really didn't do much in chapter 9. That was real. But then we moved into chapter 10, which is the bottom of our inverted triangle, talking about the trace and the determinant. And in particular, the trace of A is just the sum of the diagonal elements of that matrix. And that's, it really doesn't matter what basis A was written in for that linear map. It's still going to give you the sum of the eigenvalues of that matrix A. That's the trace. And if S and T are compatible, and let's just say they're square, then the trace of ST, well, they are square since they're both operators on the same vector space V. So now the trace of ST is equal to the trace of TS, and the trace of their sum is equal to the sum of their trace. And we also have then this formula for the determinant. That's what the vertical lines are meaning. That's now equal to the product of the eigenvalues of that matrix. And that immediately allows us to see that the matrix is invertible if and only if this determinant is non-zero, or we do not have any zero eigenvalues. If you have any zero eigenvalues, then you know you can't invert that matrix. We didn't cover this necessarily in class, but it might be a useful result for you at some point in the future if you're looking, let's say that now A and B belong to the same set of matrices, they're n by n, then the determinant of A times B is equal to the product of the determinant of A and the determinant of B. That's the yellow book. That's Axler. That's the 10 chapters of Axler. Then we have the first 2 chapters of Frank's, but I'm going to refer you to the last 2 lectures. That's basically the last content that we have for Frank's. And I don't want to repeat that. We don't have another 150 minutes to talk about Frank's. So I will say that that's brings us to the conclusion of this review, but I hope that now you have a bigger picture of the class, and as you're studying, you can start to say, oh, that's chapter 3, or oh, that's chapter 5, or oh, that's chapter 6, or what are inner products? Oh, angles and lengths. Or you have a high altitude way of thinking about some of these concepts. That's what I want you to possess. And then going into the final, I think working on the final will make it easier, or you'll have a better insight into the problems that you're working on. That's the plan. Any questions, last minute questions? Good luck.